Welcome to Consumer Times, your go-to source for insightful discussions on consumer trends, environmental concerns, and sustainable living. Today, we delve into a crucial topic where, as in the realm of organic pure materials, maintaining the highest levels of purity is essential for various industries, including pharmaceuticals, chemicals, food production, and electronics. However, achieving absolute purity is often challenging due to the presence of non-structural impurities. These impurities, although sometimes present in minute quantities, can significantly impact the functionality, stability, and performance of organic materials. In this article, we will delve into the concept of non-structural impurities in organic pure materials, their types, sources, effects, and the methods used to detect and eliminate them. Before break it down, please don't forget to like, share, and subscribe to Consumer Times to motivate us. Non-structural impurities are unintended chemical or physical entities that contaminate organic pure materials. These impurities do not alter the core molecular structure of the substance but exist as foreign particles or unwanted residues. Unlike structural impurities, which may involve changes or alterations in the molecular backbone, non-structural impurities originate from various sources during synthesis, processing, handling, or storage. Types of non-structural impurities in organic pure materials. Non-structural impurities can be broadly classified into the following categories. 1. Residual solvents. Solvents used during the synthesis or purification of organic compounds often leave behind residues that may be challenging to remove entirely. Common solvents include methanol, ethanol, acetone, and dichloromethane, which, when left in trace amounts, can impact the quality and safety of the final product. 2. Unreacted starting materials. Incomplete reactions or improper purification steps may leave behind unreacted precursors or reactants in the final material. These residual reactants can compromise the effectiveness and stability of the organic compound. 3. Catalyst residues. Many organic syntheses use metal or non-metal catalysts that facilitate the reaction. If not adequately removed after the reaction, trace amounts of these catalysts can act as impurities and affect the properties of the organic material. 4. Byproducts and degradation products. During chemical reactions, side reactions may occur, leading to the formation of unwanted byproducts. Over time, environmental factors such as heat, light, and moisture can cause degradation of the organic material, producing impurity residues. 5. Moisture and water content. Organic materials are highly susceptible to absorbing moisture during handling and storage. Water content in organic compounds can affect their stability, performance, and efficacy, particularly in pharmaceutical and electronic applications. 6. Dust and particulate matter. Contamination during processing or handling can introduce dust particles and other foreign substances, compromising the purity of the material. Sources of non-structural impurities. Non-structural impurities can originate from multiple sources at various stages of the material's life cycle. Understanding these sources is critical in minimizing contamination. The most common sources include synthesis and manufacturing processes. Residual solvents, catalysts, and unreacted starting materials may remain in the final product if purification is inadequate. Variations in reaction conditions or incomplete conversions contribute to the accumulation of these impurities. Storage and handling. Improper storage conditions, such as exposure to humidity, light, and heat, can lead to the degradation of organic compounds and introduce moisture or particulates. Contamination can also occur during handling, packaging, and transportation. Packaging materials. Packaging materials can leach unwanted substances into organic materials, particularly if stored for prolonged periods. Environmental exposure. Environmental contaminants such as dust, gases, and airborne particles can be introduced during processing or packaging, compromising purity. Impact of non-structural impurities on organic pure materials. Even trace levels of non-structural impurities can have profound implications on the performance, safety, and quality of organic pure materials. Some of the key impacts include 1. Altered physical properties. Impurities can modify the melting point, solubility, and crystalline structure of organic compounds. This alteration can affect the material's functionality, especially in pharmaceutical and electronic applications. 2. Reduced efficacy and stability. In pharmaceuticals, non-structural impurities can diminish the potency and shelf life of drugs, leading to reduced therapeutic efficacy. In chemical processes, impurity-laden compounds can reduce yield and efficiency. 3. Potential toxicity. Certain residual solvents, catalyst residues, and byproducts may introduce toxic or harmful effects, posing health risks to consumers. 4. Degradation and deterioration. Impurities can accelerate the degradation process, leading to loss of quality and effectiveness over time. Detection and analysis of non-structural impurities. To ensure the purity of organic materials, robust analytical techniques are employed to identify and quantify non-structural impurities. Commonly used methods include 1. Gas chromatography (GC), ideal for detecting residual solvents and volatile impurities, provides high sensitivity and precision for trace level analysis. 2. High-performance liquid chromatography (HPLC), used to identify unreacted starting materials and byproducts, allows for the separation and quantification of multiple components in a mixture. 3. Mass spectrometry (MS), combined with GC or HPLC. MS is used for detailed analysis and identification of impurities at trace levels. 4. Karl-Fischer titration, a specialized method to detect and quantify moisture content in organic materials. 5. Inductively coupled plasma mass spectrometry (ICP-MS), effective for detecting and quantifying trace metal impurities, such as catalyst residues, shield minimizing and controlling non-structural impurities. Controlling non-structural impurities requires a multifaceted approach that includes optimizing synthesis protocols, refining reaction conditions and purification methods to minimize byproducts and unreacted materials. Effective purification techniques, employing advanced purification processes such as distillation, crystallization, and chromatography to ensure high levels of purity, stringent quality control measures, implementing robust quality control systems throughout the manufacturing process to detect and eliminate impurities, proper storage and handling practices, ensuring appropriate environmental conditions, packaging materials, and hygiene practices to prevent contamination. Non-structural impurities in organic pure materials, although often present in minute quantities, can significantly impact the quality, safety, and efficacy of the final product. Industries that rely on high-purity organic materials, such as pharmaceuticals and electronics, must adopt stringent protocols for impurity detection, control, and elimination. By implementing advanced analytical techniques and maintaining rigorous quality standards, manufacturers can ensure the production of high-quality organic materials that meet industry benchmarks and protect consumer safety. If you found this discussion insightful, don't forget to like, share, and subscribe to Consumer Times. Let us know your thoughts in the comments below. Until next time, stay informed and stay sustainable.